Okay, thank you very much for the kind introduction. So, good morning, and it's my privilege today to be here in Seoul, Korea, and tell you a little bit about the work that I've been involved with at Amazon Web Services in developing quantum computing hardware. So, as my title indicates, although I'll talk a little bit about what we're doing at AWS, there's a broader, bigger message that I want to relay this morning. And that is that we're entering a new era of quantum computing, an era in which we are beginning to tackle some of the most difficult and challenging problems associated with the complexity of building error-corrected hardware. And this harkens back to the type of challenges that integrated microelectronics faced in the 1960s and 1970s. And at that time, they called that integration problem the tyranny of numbers. And so I like to call this new challenge that we face the quantum tyranny of numbers. And I'll tell you a little bit about some of those challenges we face and some of the opportunities we have in the coming years. So before I dive in, one of the first things that I usually get asked about with this type of work is just what is quantum computing? So I think Richard Feynman said it best in his own colorful way nearly 40 years ago when he said that nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. And so if we think about what Feynman was getting at, and why he felt that quantum systems were going to be important in modeling some of the most and simulating some of the most difficult problems in nature, we can just consider the challenges in representing a quantum state of as a function of number of quantum particles involved. So here I'm just showing the memory it would take to store a quantum state as a function of the number of quantum particles. And so you can see this exponential increase in the required classical memory, digital memory, in storing that quantum state. And just to give you an idea of the scale, that as you get out to a few hundred quantum particles, you would require more memory bits than the number of atoms in the observable universe. All right? So that level of complexity underlies the power of quantum computers. But that's not the whole story. It's a very simple picture. It's really important to understand that what Feynman was getting at is that a classical computer or digital electronics, a quantum computer is not a classical computer. It's not just a faster classical computer. It's a computing system that can compute a much richer, potentially more challenging set of class of algorithms. And it does it in its own particular unique way. So the first types of problems that we imagine quantum computers being useful for, again, harken back to what Feynman was talking about, and would be in the area of physics or chemistry or material science. There we're dealing with quantum chemistry, with electronic bonds, with electronic orbitals. And it's a much more natural, or it is a very natural place in which one would utilize a quantum computer to do advanced modeling. But there's other very surprising areas, which we've learned over the last few decades, where quantum computers may also be relevant, in areas such as cryptography. There's also areas that we are still looking at trying to develop quantum algorithms, like in optimization problems, or even in potentially machine learning. So the second question I typically get asked after I get asked, what is a quantum computer, is how do you build a quantum computer? What's inside a quantum computer? And so I'm just showing you here in schematic form the guts or the overall system architecture of most quantum computers. So again, referring back to Feynman, you can build a quantum computer out of almost anything, all right? Every physical system behaves quantum mechanically and could, in theory, be used for the internal elements of a quantum computer. But all of them share this very similar architecture. One has a quantum processor that has quantum elements, call them quantum particles, that you'd like to control the interaction of in order to perform some dedicated computation. But in order to do that, we need to wire up these and control these quantum objects. And so we shield this quantum processor with all the quantum elements in it as much as we can from the environment, and then we only let in very specific control lines, okay, into that environment. And then those control lines, this is our classical I/O from the quantum computer, they get connected up into some, typically optical or electronic, specialized electronics that can generate these control signals. And then above that, you have a classical compute layer, both in hardware and in software. So just stepping back for a moment, I think it's really important as I go through, as I move on to the rest of my topic, to have this picture in mind, that a quantum computer is much more than just this quantum processor with the quantum elements. It's this entire classical infrastructure that sits on top of it. Okay, so now let's go in and talk a little bit more about the guts of a quantum computer. So the type of quantum systems that we're developing, or quantum computing hardware we're developing at Amazon Web Services, along with many other efforts around the world, are what are called superconducting quantum circuits. And so I'm not going to go into the gory details of what a superconducting quantum circuit is, but I'm going to try to give you a little bit of the flavor of what these circuits are. So one of the first elements you learned about in school is an electrical oscillator. And so that involves an inductor and a capacitor. And an inductor is sort of a delay element for current, and a capacitor is sort of a charge storage element. And by connecting these two elements together, you actually get an oscillating current and charge, where the current oscillates through the inductor and produces charge on the capacitor. And it does this in a very periodic way at a well-defined frequency. So these sorts of oscillators are in a lot of our microelectronics that we use today, like our cell phones and our et cetera. Now, if you add to that electrical oscillator one simple element, okay, it's called the Josephson junction, which consists of a bilayer of superconducting thin films separated by an atomically thin electronic barrier, dielectric barrier. And this circuit element, when replacing the inductor, forms another type of circuit element that actually can be can form the basis of a quantum bit, or a quantum element for doing processing. For short, a qubit. And this is one of the more popular qubits that are used in superconducting quantum circuits. So what's special about superconducting quantum circuits is not just that we can create these very interesting elements that actually mimic the quantum properties of other more exotic quantum particles, but we can do that using wafer-scale microfabrication. There's a flexibility in the way that we produce these, so we can actually create all sorts of different circuits and create new types of quantum bits or qubits. And they're fast, all right? These electronic circuits operate at sort of gigahertz frequencies, and you can imagine processing information at sort of nanosecond timescales, similar, again, to the electronics that we find in our conventional classical technologies. The only difference is that, one, they use superconducting metal films, and the superconducting films are used because they reduce the dissipation, the ohmic dissipation that occurs, and that ohmic dissipation would just spread the energy out into other degrees of freedom, and in a quantum system that would cause a corruption of the data. But they also operate at extremely low voltages, typically microvolts, and so it's about 1 million times lower voltage than the digital electronics you have in your conventional electronics. So these two features, low loss and low voltage levels, along with these nice properties, define this type of superconducting quantum circuit technology. And so similar to most other microelectronics, superconducting quantum circuits start out as a silicon wafer, shown here. And by growing superconducting thin films on top and stacking them on top of the silicon wafer, and then patterning them in special ways to form different circuit elements, one can form the Josephson junctions, the wiring, the conductive wiring, and other resonant elements on these circuits. This is a zoomed-in picture of one of the processor dies on the silicon wafer. And you can't see the qubits. The qubits actually sit at each of the intersections of this, what looks like a map of a roadway. And then the other elements are actually used to control those qubits on these devices. And just for scale, you can see that these are actually relatively large electronic circuits physically. Okay, so I've told you that we have these superconducting quantum circuits, that we can print them at wafer scale, that we can design quantum bits or qubits that can form the basis of a quantum processor, and they have all these great properties. So the third question I typically get asked is, why don't I have a quantum computer today? Now, where's my quantum computer? And so you hear about it in the news probably every single day. There's lots of media reports that talk about quantum computing will change our lives. It'll be here tomorrow. You're going to have quantum computing and AI on your phone pretty soon. And so quantum is coming. It's going to change the world, but you actually need to read the fine print. All right? So it turns out that despite all that hype you may read about, we are far from a practical, useful quantum computer. That isn't to say that there haven't been huge advances made in the last few decades as we've been trying to build quantum computers, but we have to keep in context where we actually are on that road. And so why don't we have our quantum computers today? Well, there's a simple answer, and the simple answer is noise. So quantum systems have a special language they use to interact called quantum entanglement. And so this dance of quantum particles produces correlations in those particles that there's no classical analog of. It's a much deeper, richer set of correlations that one can obtain between the quantum bits or the quantum elements. And any part of the environment, even this sort of ping pong balls shown here in this cartoon, that interact with your quantum system can disrupt that delicate quantum entanglement dance and corrupt the computation you're performing. And so quantum computers are extremely sensitive, because they rely on this quantum entanglement, to any interactions with the environment. And that's at the heart of what is limiting our ability to build good quantum computers. This environmental noise that we try to shield our quantum systems from as carefully as we can gives rise to to errors in our computation, because we're disrupting the sort of controlled quantum entanglement we're trying to utilize. So it turns out that we can classify the effects of that noise in two different ways on our quantum bits. So in the first way, we can classify these noise-induced errors as what are called bit flips. So these are types of errors that occur in our digital electronics. And here I'm representing a quantum state of a qubit on what's called the Bloch sphere. You don't have to know don't have to know those technical terms. Just know that in quantum mechanics, when I represent a quantum bit of information, I have states that it can represent which are like the digital 0 and the digital 1, which are on the poles of this sphere. But I can also, through superposition, so quantum mechanics allows any combination of 0 and 1 to be a valid state. I can represent, every one of these points on the sphere represents a valid state of the quantum bit, even simultaneous mixtures of 0 and 1. And so the bit flip is one form of error in which I may be sitting at the 0 or 1, and then all of a sudden my quantum system flips from the north to the south pole, or from the south pole to the north pole. Completely analogous to the digital bit flip we have in our digital electronics. But there's a purely quantum type of error that we need to deal with for quantum systems. And this is the phase flip error. And so as I mentioned, on the equator, okay, the states that correspond to the equator here are actually mixtures, equal mixtures of 0 and 1. So it's the quantum system, this qubit is in a state of 0 and 1 simultaneously. And those states live on the equator, and you can think of this phase flip error as a flip across the equator, where I might have 0 plus 1, okay, some well-defined phase between 0 and 1. And then on the other side of the equator, I have 0 minus 1, a different parity of superposition. And so this pure phase error, okay, is a pure quantum error, this phase flip error. And so it turns out that I can digitize all errors, all quantum errors, in these two forms. But surprisingly, just the fact that I have this additional class of errors that are purely quantum, so I don't have phase flip errors in my classical electronics, just this very simple fact is what makes implementing error correction and mitigating the errors in our quantum computers so difficult. All right? That one little simple fact. So let's look at what progress has been made over the years in trying to combat these types of errors inside of quantum computers. So if we go back 15 years and we ask, okay, at that point we'd become masters of the quantum domain. We could actually manipulate small numbers of qubits, what we felt at the time, very precisely. And we were still thinking quantum computers, that was sort of a dream at that point. But the reason was because the errors that were produced, we had an error about every 10 operations, about 10% error rate 15 years ago. So the whole community worldwide, worked very hard for 10 years. And then in those 10 years, they were able to reduce that by a factor of 10. So they could actually have error-free operation on their quantum bits for 100 operations, so a 1% error rate. And then for the last 5 years, we've again seen more progress, and this is reduced by another factor of 3 to about, the state-of-the-art enables us to realize operations on our qubits that are error-free for about one in a few hundred, so about 0.3%. But where do we need to be for the applications I mentioned? So let's say synthesizing a new type of material, or doing some calculations with chemical accuracy of molecules or chemical reactions. What would it take to do some of those early problems that I said were nearer term? Well, we need something like 1 trillion error-free operations to do those sorts of calculations. This is a huge gap between where we are today and where we need to be. So clearly, this approach of just continuously improving the way we control the physical qubits is going to take us many, many decades. If you just extrapolate this, even if it was possible, it might take 66 years, 70 years, 7 decades before we would reach this sort of level of accuracy. So, should we just give up? That seems pretty daunting, even for someone like myself that would really like to see a quantum computer exist. That seems like a very daunting task, 9 orders of magnitude between where we are today and where we need to be. But it turns out we don't have to give up hope. In the 20th century, mathematicians and physicists figured out how to deal with noise in classical systems, how to develop error correction systems that would deal with those errors. And a very good example of this is in high-density data storage. So all of your classical data, all the data you store in, let's say, AWS's cloud, gets stored on high-density data storage. And it might surprise you to realize that the rate at which this data storage creates errors when it writes your data is about 1%. Very similar to the error rates that our quantum computers are making. And so that's not going to be a viable technology, so how do we get around it? Well, by adding just a little bit of redundancy, so taking our n bits of data and adding about 30% more bits, and spreading the information over that additional redundant set of data bits, and encoding the information using special mathematical formulas, allows one to reduce the errors upon decoding because of that tiny amount of redundancy from 1% to about 1 part in 10 to the 16. So it improves the fidelity of your read and write by about 10 million billion times. Pretty amazing. That's classical error correction. So what about quantum error correction? Well, it turns out we also know how to do that. And we've known how to do quantum error correction for at least several decades, in theory at least. And so if we just think about a quantum processor, and again, I'm at the physical level, you have some array of qubits, which I'm representing by these green circles. You can control these qubits either independently or en masse already today. And these qubits can connect to each other to perform logical operations or computations between the qubits. So we know how to do that. And that's what, and you have different connectivity graphs and different layouts, but many of them look similar to this inside your quantum processor. And that's at the physical layer. But when we perform error correction, we need to abstract away this physical layer, and we need to think at a logical layer or a software layer. So we can do all of this in software. And there we control not individual qubits, but we control them in blocks, okay? And these blocks of physical qubits are what give us our redundancy. And we encode, we sort of hide our quantum information within that block of physical qubits. And if we do it carefully enough, then we can actually protect that information even in the presence of noise. All right? So it's at this logical qubit level that we perform quantum error correction. And it can be done in software. It's still built on a similar physical layer. But there's a connection between how well this can be done depending on your choice of the physical layer, as I'll mention later in my talk. So the problem, I said that theoretically we knew how to do this. So then if we theoretically know how to do this, we can make all these physical qubits. Again, why don't we have our quantum computer? Well, the reason is because the overhead, I told you that for good classical error correcting codes, you only need about a 30% overhead to obtain tremendous gains in the reductions in the logical error rate. But this one fact that I have bit flips and phase flips, not just bit flips, means that my quantum error correcting codes are much more challenging to implement. They have what are called much higher thresholds, meaning I need much lower physical error rates for them to be useful. And they use up many more resources. They need more physical qubits, more redundancy. And so to give you an idea, if we were to improve the physical error rate by another factor of roughly 10 from where we are today in our qubits, we might need an overhead per logical qubit. We might need about 1,000 physical qubits, all right, using conventional error correcting techniques. So that's the challenge we faced maybe a few years back. People have now been figuring out how to reduce this overhead, but that's one of the big challenges we face. So just summarizing, quantum computers don't exist today. The challenges we face, practical ones. The challenges we face today are related to implementing error correction to combat the errors. We have a 9 orders of magnitude gap to overcome, so it's a big challenge. Because we have to implement error correction, it means we have to scale our systems much larger because we have to add this, large factor of redundancy into the system. So that brings about scaling challenges. And then finally, something I didn't mention, but it's really important to keep in mind, is that although quantum computers have an algorithmic advantage over classical computers, as I mentioned, in some applications, you still need to clock them pretty rapidly in order to, at least today, as we know it, to perform computations of practical import. All right? And so, roughly speaking, you might need to, clock your systems maybe at a megahertz or 100 kilohertz in order to perform, at least as we know them today, algorithms that would be provide quantum advantage and practical utility. But that's something that, again, will be important as we start to address 1 and 2. So here's a pretty typical roadmap for how one would develop a error-corrected quantum computing hardware. It starts with a logical qubit memory. After you can make a good memory where it can store quantum information very efficiently, then you need to actually work on how you perform logical operations with those logical qubits. Those are logical gates. We're sort of at step 1 and step 2 right now. And then eventually these error rates we get really good at making qubit memories, and we get really good at doing logical operations, and ultimately we do reach this fault-tolerant limit where we can actually perform the calculations with high enough fidelity, or our operations are high enough fidelity to perform those calculations of interest. And then we need to scale our system. Once we reach this fault-tolerant limit, we need to start scaling up to, not just in physical qubit number, but we need about 100 to 1,000 logical qubits to do interesting problems, just the early problems. These are logical qubits. But that just gives you an idea. If our qubits started out really good, we would only need 100 or 1,000, right? But because of the overhead, this might be 100,000 or 1,000,000 qubits that we might need. And then we want to speed things up, and then we want to keep increasing. And we can target, at this point, we can start targeting interesting applications, and then widespread applications as we start to scale beyond, let's say, 1,000 logical qubits. And we have them operating and clocking them at high speed. But let me step back. I mentioned that we're at sort of not step 0, but step 1 as a community. We're really trying to work to develop architectures that can employ quantum error correction with high fidelity. And we're trying to figure out how to scale those systems more efficiently. So the approach we're taking at AWS is from the ground up designed to address this error correction problem. So we looked across all the entire field, and we really looked at what type of physical hardware is going to give us an advantage when it comes to building out error correction. So not thinking about early gains we can get from making advances at the physical qubit level, but what is going to be an architecture that can implement error correction at the logical qubit level more efficiently. So I mentioned this conventional superconducting circuit qubit at the beginning of my talk, the transmon, which has a Josephson junction, replacing the inductor, and a capacitor. It turns out this transmon qubit is what's called unbiased. It is just as sensitive to bit flip errors as it is phase flip errors. And I told you that if you have both of those, then it makes your error correction much less efficient, or much more challenging. So at AWS, it turns out that there's another approach that's been known for a couple of decades, based around just the simple oscillator I told you about at the beginning. So we can build these microwave oscillators using very similar fabrication techniques. And if we add to them a stabilizing circuit that actually includes some of these nonlinear Josephson junction elements, all right, then we can form a new type of qubit called a stabilized cat qubit. So let me tell you about how a stabilized cat qubit works and why it might be interesting and important from an error correction standpoint. So the analogy I like to use is that of a pendulum or a swing, maybe a child on a swing. And so imagine one state of this oscillator being the pendulum or the swing in which we swing it to the right with an amplitude plus alpha and then release it. Okay? And it just oscillates back and forth. It's the current and charge that are oscillating in our electronic circuit. And then I can also move the swing to the left, call that with amplitude minus alpha, and then release it, and it'll oscillate back and forth. Both those states are perfectly fine, and we understand them classically. Now, it turns out in quantum mechanics, I can have both left and right swinging going on simultaneously. All right? And we call these cat qubits in analogy to the dead or alive state of a cat, because we have this left and right oscillating, or sets of oscillations with plus alpha and minus alpha. So this is an equally valid state inside of our oscillators. Now think about how physical noise impacts the pendulum. So imagine a child in a swing that's swinging with amplitude plus alpha, and a child in a swing that's swinging with amplitude minus alpha. And let's say a gust of wind comes up and blows that swing. Well, for small amplitudes, I might actually kick the swing from the right side to the left side, with some small probability. But now if I increase the amplitude, I make this cat larger and larger and more macroscopic. All right? I make the oscillation amplitudes larger. Then the probability that I'll kick from the right side to the left side becomes less and less likely. It turns out exponentially less likely, because the physical noise sources involved in nature are local in that way. So we take advantage of the way noise comes into systems physically, and we realize that, oh, well, this might actually, and if we not have even in the presence of noise, it'll become exponentially suppressed, this kick from the right side to the left side state. And if we identify this state here, this plus alpha state is our 0 state, and this minus alpha state is our 1 state, then we've suppressed bit flips exponentially. And that's how these oscillator-based circuits work. You can actually eliminate one type of physical error exponentially with a very small penalty in the other type of error. And so it's heavily noise biased. It has almost no bit flips, and it has still has the presence of phase flips. But now my challenge from a quantum error correction standpoint looks a lot more like the classical challenge, where I just have to use error correction to protect against one type of error. And that little simple property of these systems means that the error correction actually is tremendously simplified and can realize large gains in the overhead reduction. This is just showing you stabilized cat qubits that we built at AWS in the lab. And this is showing the bit flip time as a function of the cat amplitude. And even for an amplitude just a few times that of the smallest quantum amplitude you can make in an oscillator, about 4 times, you can actually increase the bit flip time by 5,000x in these systems. And so back in February, we released our first quantum prototype chip. We called it Ocelot. Ocelot's a type of cat. This chip is based upon cat qubits. Now this is a very simple prototype, but I think a very powerful demonstration. It utilizes all of the advanced techniques for integrating superconducting quantum circuits together, but it has this very unique type of qubit that is ideal, in some sense, for implementing error correction, or it has this advantage in its biased noise capability or property. So it's a very simple demonstration of a single logical qubit memory, all right? But it utilizes these noise biased qubits with about a factor of 5,000 reduction in the bit flips. And in doing so, it reduces the overhead by about a factor of 5 to 10x in implementing error correction. Okay, so clearly there's a lot of opportunity in going forward as we enter this era of quantum error correction in hardware. There's a lot of opportunity to rethink what type of physical systems and architectures make the most sense for building these types of error-corrected quantum hardware. It had not been, I would say, even though the theories had been around, it had not been a particular point of emphasis. There had been a lot of theory work, but it was such a big challenge, and I think people were just sort of pushing it off. Maybe we can build smaller, systems that don't rely on error correction. I think as a whole, the community is now accepting that if we're going to actually build systems that can perform the most challenging and most interesting computations, we're going to need to implement error correction. So we need to address it head on, but in doing so, we're going to run into the next wall. So we're going to be looking at these architectures for error correction. They're going to require large overhead. We're trying to figure out how to build an architecture that has reduced resources. But it's going to be a challenge to get to 100,000 or 1 million qubits, all right, which may be required. Maybe you'll be able to reduce that a little bit. But it's going to be very similar to the type of complexity that people faced in microelectronics industry back in the 60s, as I mentioned. And so Jack Morton, amongst others, coined this term, the tyranny of numbers, when he was thinking about the challenges in trying to wire up, as he mentioned, just if you think about it, hundreds or maybe thousands or tens of thousands of electronic devices. Well, we figured out, we've mastered the numbers, the tyranny of numbers, right, in the classical domain. We figured out how to wire these things up, but at the time, it was really challenging to think about how to address that complexity problem. So what I'd like to say is that we also face a similar quantum tyranny of numbers. We will face it. We're beginning to face it. And it's going to be, we can learn from what we've done with classical systems, but we also need to take into account a number of other specific challenges for quantum systems that would need to be addressed. The first is that because we need to implement quantum error correction, because our hardware is fundamentally noisy and error prone, every part of the hardware, every gadget in the quantum domain is noisy and error-prone. We need to control every qubit, every cycle. That requires a far different wiring architecture than our standard, like von Neumann architecture that we use for classical computers, where we can sit and idle some of our bits, have memory, pull things from memory. There's no longer a nice static memory that works well for us, right? We're going to need to implement error correction for our memory as well. And so we can't just use spectator qubits and only control a small fraction of our qubits every clock cycle. We're going to need to talk to every qubit, physical qubit, every clock cycle likely. That is a huge difference in architectural challenge than, let's say, the classical systems, where people figured out how to have many, many transistors and digital bits on our processors, but they would flow information in and out over buses and over other different channels. And so therefore, the number of control wires that come out are far fewer than the number of transistors on a chip. Far, far fewer. So you might have a chip with 100 billion transistors on it, and you might only have like 1,000 connections to it. This may not be possible for quantum systems. So that's going to be a big challenge. The second issue is that the way we wire up our qubits is even more sensitive than the classical domain. So in the classical domain, we care a lot about the power it takes to drive different control lines. And that was also a big part of the way that what people thought about when they were developing and scaling out microelectronics, CMOS in particular. What did the power and the scale look like as a function of the wiring density and things like this? Here we've got to worry about, we need really lossless connections between our qubits, because any loss will cause a connection to the environment, which will then cause errors in our system. We also need to limit the amount of crosstalk if we're going, and so this is similar to in the classical domain. But these two things, this quantum coherence of our wiring is another big challenge that goes beyond what we have to deal with in the classical domain. And then finally, we may need non-local coupling. So I talked about, it's very natural. Physical systems connect together locally. Doing non-local connections is not easy. Physical systems are just naturally local. And so non-local coupling is important because it may allow us to improve the hardware efficiency of error correction. So all these three elements mean that quantum systems, the quantum tyranny of numbers is a potentially much bigger challenge than just the tyranny of numbers we faced with our microelectronics work. Okay, so I'm going to end my talk here. I'm happy to take any questions after the talk about some of the more technical details. But I hope I've given you, well, before I get there, how are we going to address this in terms of key areas for innovation, or where are the key areas of innovation? So I'm going to talk primarily about solid-state quantum systems. There's a version of this that also maps onto other quantum systems that are not solid-state based. But one thing I want to mention in terms of trying to address this quantum tyranny of numbers is that we need to go back and we need to invest in materials and device fabrication. Yes, we can ride the coattails of the semiconductor industry, especially for superconducting quantum circuits, but that's not going to be enough. We definitely have to invest in things like atomically precise interfaces and defect-free superconducting surfaces and other surfaces. These are the same things that we've put billions of hours into to engineer, let's say, the gate in a transistor. We need to do the same thing for the Josephson junction, for instance. That is how we're going to build the real technology. There's going to be no simple way around this. We need to make a manufacturable, high-performance technology. And today, the way we make our Josephson junctions were invented back in the 70s. All right, so we need to take and build new techniques and work with new materials. There's just no doubt in my mind. The second thing is, where we can, again, perhaps in this case, ride the coattails of the microelectronics industry, is for as we build larger and larger systems and as we address this scale-out problem, we can leverage the 3D chip stacking techniques that are being developed for instance, for AI chips, where you want to connect your high bandwidth memory to your logic Same sort of challenge, opportunities exist there, where you're trying to densely pack chips and integrate them together. We can develop similar superconducting technologies, for instance, leveraging the things that are being developed for new chipsets and 3D chip stacking. And then finally, the control integration problem. There's opportunities to integrate the classical control directly in with the quantum processor. For instance, using superconducting digital logic in the case of superconducting quantum circuits. And so that could tremendously free up and simplify this wiring problem. So these are all very heavy investments, but key areas for innovation that will really, I believe, produce a practical quantum computer in the quickest amount of time. And they all relate to this quantum tyranny of numbers problem. Okay, now I'll tell you about my concluding thoughts. So I think one of my main points here, and it's been known within the scientific community, probably many of you in the audience, that we're entering an era of quantum error correction, not just in theory, but in practice. And what is that going to mean? We're already seeing it. You've heard a lot of recent announcements from companies like Amazon and others about these these big advancements. It's hard to decipher what's real or not, but the reason you're hearing about many of them is because we're actually starting to implement quantum error correction in practice. This is a huge paradigm shift, and it's a huge opportunity, and you're going to see a very rapid improvement in performance in quantum computing systems because of it. I like to think of quantum error correction as an exponential lever. Linear improvements in the underlying hardware give rise to exponential improvements in the logical performance, logical qubit performance. So you're going to see significant advances in the next 5 years, I believe, even if we don't reach all the way to fault-tolerant practical quantum computers in those 5 years. This is going to be a very exciting era. I've already talked about the fact that at full scale, it's going to require improvements in manufacturing and innovation in the control wiring, this quantum tyranny of numbers problem. We have to take this seriously now if we're going to be ready in 5 or 10 years. And I think as the hardware evolves, as we see this exciting improvement in performance due to quantum error correction, as we start to scale out our systems, although we may not in 5 years see a practical quantum computer that can go and crack RSA code, a 2,000 or 3,000 bit code, we are going to see exciting emerging opportunities. And one example that I like to point to, I think, it's not something that I can say rigorously, I can write down mathematically and prove to you, but there's opportunities, for instance, in AI and machine learning, and not in the way you may think. So these quantum computers that we're going to be building in the next 5 years are not going to be, let's say, practical, but they're going to perform computations that no classical system can produce. They're going to produce data sets that no classical computing system can produce. With those data sets, we can feed that into an AI model that knows quantum mechanics. It's easy to train an AI model on quantum mechanics. And it's going to be able to use that data to tell us how to build better quantum computers, how to build better error-correcting codes. I think there's going to be a virtuous cycle that emerges in the next 5 years, and we should look for it and we should take advantage of it. Okay, I'll end there and happy to take any questions. Thank you very much.